recording works. Seems to be recording. Stage is all yours.
Thanks a lot. So thanks a lot for coming. I want to talk to you about some cool new ideas or packages that do serialization in Haskell. Before we actually dive into anything, there are actually two different use cases of when people talk about serialization. It's kind of overloaded. One is you want to serialize in known format, something like media files or whatnot, and it's already a defined format, and it's has some spec which you need to follow. And the other one is you have just your own Haskell data type, and maybe you want to ship it off to a different machine or a different Haskell process, or maybe you want to save it for later use. And they are slightly different, right? You can do different tricks, say, too, because you can use different formats for your own things, whereas one is very well specified. And this talk is very much going to be focused on the second point, where you have your own Haskell data type and you want to serialize it, you want to do something with it. And there are different approaches to it. And so the whole presentation is going to basically follow, it's going to be a tale of three packages. And so I'm going to start with binary, which is basically the de facto standard for how do you do serialization in Haskell. And it's going to be a bit of a point reference. And then the new exciting things, the CBOR and store packages. I'm going to call the second one just CBOR because the name is too long. But there's a ticket about coming up with a better name, so feel free to chime in. So what I'm kind of after in this talk is trying to answer the question, what should you use? If you just want to do something with your data type, what are the caveats? What are the things that you should keep in mind? And what is the decent default? And then we're going to kind of look into what are the differences, both in terms of high-level philosophy of how they approach the task, as well as how they implement the actual serialization. And the second part is actually quite interesting because there are those two new packages approach serialization quite differently, and there are some interesting ideas that you might not expect. So, start with binary. By the way, if you have any questions on the way, just shout. So, starting with binary, it's one of the kind of probably older packages. I'm looking at the Git repository. The first commit is December 2006, and it was uploaded already to Hackage in 2007. It's very widely used, very widely known, very well tested, and bunch of optimizations and thought went into it. But as you'll see, there are some fun facts, tricky facts. So the interface is kind of pretty simple. If you think if I'd ask you how could you imagine an interface for a serialization package, that's probably not too far off. And so you have basically two things: either you serialize or deserialize. Either you put some value into bits, or you get it. So both of those put and get are actually monads. And I'm going to kind of look mostly. Yeah, go for it.
Is this asynchronous on decode, correct? Does the read throw an exception?
I think so. I think there's also another version of the code with different with something like either. I don't know. I think there's more. I just picked it up as an example. So the put monad, I'm going to kind of have a look at a bit more on serialization. And when you want to serialize something, basically what put monad is nothing else than just a writer monad. So that wraps a builder. So there's a monoidal builder inside, and then you just append things to it. And the monad is mostly to have a nice kind of syntax where you can semi-imperatively say write this, write that. The interesting part though is that nowadays the builder and the binary used to have its own builder, but nowadays it's switched completely to the byte string builder, which I found kind of interesting and didn't expect. So basically the whole module just re-exports the byte string builder. And if you don't know what this byte string builder is, it's kind of popular, it's all about the lazy byte string. So here's a short reminder, where the lazy byte string is defined just as a list of strict byte strings. So it's like, you basically chunked a byte string into a series of like arrays, basically. And byte string builder is, as I mentioned, completely based on the idea of monoid, where you just append things into it. So how does it look inside? This is going to be useful because it's going to be we're going to talk about it again in one of the other packages. So basically the idea is that have you heard of difference lists? When you want to append lists, it's kind of expensive if you just operate on lists. But if you use function composition, then it's basically then it's cheap, then it's one. That's kind of the same here, where you can you have a builder and you're going to have a builder that is going to say write bytes for one thing from Word, from something else, and then if you want to combine them, append them, then it's going to be just composition that does those two things. But it's slightly more complicated than the difference list in terms of this build set. So the problem is, basically the way this works, as I mentioned, there's this lazy byte string. So you have a fixed size buffer, and you want to write into it. And you write, but at some point you might run out of space. And that's basically the whole idea of this build step, where buffer range is going to tell you how much space is left and where you can write. If something already wrote, you might need to point into the middle of the buffer. But if you did run out of space, then you can return this build signal, which tells the whole infrastructure how many bytes you've written, and maybe you need another of those strict byte strings to be allocated, and then you can continue writing. So it's slightly more complicated loop where basically you allocate a buffer and provide this buffer range, check if you're fine. If not, you want to allocate another one and continue. Otherwise, you just write and continue to the next function. So that's basically was the byte string layer. So if you have just byte string and you want to write bytes, that's what you would use. But binary provides things on top of it, right? So you don't actually want to do, say, if you want to serialize Word in big endian, you don't want to manually do all the byte shifting and so on. So binary builds on top of that, so uses the builder inside, but provides a bunch of functions that allow you to do things slightly in a slightly nicer way. And it actually has a layer of its own smarts, trying to avoid some of the useless work. I think Simon actually wrote some of this stuff.
I wrote both of these things.
Right.
Building on previous work, but yeah, the buffer range and the bounded prim.
Yeah.
Good memories. That was actually my first open source work for Haskell.
Yeah, it's pretty cool. So the idea with bounded prim is kind of neat. So one of the problems is, as I mentioned, you need to know how much you need to write. Like, if I want to serialize something, how much space do I actually need? And bounded prim is basically trying to do that. How much space do I need? And one of the cool things that you can do is this additional information is, for instance, fusion. So those word 32s here, you can imagine them as bounded prims that are going to serialize this C1, C2. And prim bounded is going to inspect how much is needed, create the build steps, and then if everything fits nicely, gets inlined, there is a collection of rewrite rules. And if everything kicks in, then instead of checking here, oh, do I have 4 bytes so that I can write, and then go on and check again, and have another 4 bytes, and then write. What's going to happen is that you're just going to check, do I have 8 bytes, and write them both. But it's kind of awesome that it works, but at the same time it kind of depends on JC's optimizer to make sure that it actually gets in line, because rewrite rules fundamentally depend on this, right? If you don't have everything in the right shape, they might not fire. So there's this whole layer of also providing additional information, how much space is actually needed to make it more efficient. So what are some of the issues with binary? So as I mentioned, it's very well tested, and things like byte string builder are pretty well optimized. But the serialization format hasn't been thought through very well, at least in some places. And I think the most famous one is this double and fold serialization, which just takes immense amount of space and is super slow. I think that I've had some benchmarks later on that will show just how massively slow it is. And I think reading through some blog posts about the store package, this was actually one of the motivations to look into doing things a bit more efficiently. And of course, the problem is that because binary is used so widely, now changing things would be quite hard. So it's kind of stuck with the current format. And there's some other interesting trade-offs to be made, right? Where if you want to store number 1 as in 64, it's still going to take all 8 bytes. It's a fixed number of bytes for a type. And the last thing that I think, and that quite a lot of people are not entirely happy with, is this inlining. So binary is pretty heavy on it, and using binary in order to get good performance, kind of blows up the amount of code that is generated in user code. So if you're just a user, you still get a lot of compilation slowdown and a lot of bloat in terms of code size. So one of the first contenders to be the new better serialization. So here, one of the first things to note is that with CBOR, it's actually the CBOR itself is an RFC and has nothing to do with Haskell. It was created independently as basically a better way to serialize things. So what are the main things about it? It's kind of similar to JSON, except it's binary. So it's if you can think about it also to be similar as message pack. It has like a basic types, so it actually carries the type information for the basic primitive types, which means that if I give you the bits that represent the CBOR value, you're going to be able to figure out that this is a list and this is an integer and then this is a double. Whereas if I give you the output of binary, it's just bits, right? You don't have the additional tags that will tell you exactly which type it is. But there is no schema like say with protocol buffers or Thrift or something like that, where you need to define something separately in a separate language. It still just defines how to express those primitive types. And I think a fair amount of time was also spent on trying to make it small and concise. So as I mentioned just previously with binary, and N64 takes always those 8 bytes. That's it, no matter what the value actually is, even if it's just 0. Whereas here, small numbers are going to take significantly less space than the larger numbers. And so there's a bunch of tricks to do that. And another one nice kind of benefit that this is not just Haskell project. This is the CBOR itself is actually kind of a standardized way, is that you can grab libraries that are able to serialize, deserialize CBOR values in almost any language at this point. So if you want to send something to a binary that is written in a different language, that's also a possibility without trying to reverse engineer exactly what binary is doing for particular types. As I've written here, the main folks behind this is Duncan and Austin from Well5. And I think Duncan was actually giving a presentation about this in one of the Zurich hacks like a few years ago. So example, I mentioned the tricks that they play to try to make the actual bytes, the actual size of the serialized value smaller. So let's imagine that you have this abstract representation. So this is basically a list of number 44, 42, the bigger one, and a string. And the way you would express this in CBOR is that you would say first put 1 byte that indicates that this is an array and it has size of length of 5 elements. So this is just 1 byte. Then you would serialize the first number, 4, and this is still going to be just 1 byte. So instead of saying that, oh, this is going to take 4 or 8 bytes, this is just a single one. And then 42 already doesn't fit into 1 byte because there needs to be some of the space is used to indicate what type of value it is. And then there are only some bits left to actually represent the value. So 42 doesn't fit anymore, so it needs 2 bytes. And similarly with the bigger numbers, you can see that we have a tag and a few more bytes. And in a huge kind of arbitrary precision case, what you're going to get is that there's going to be a special tag that indicates this is an integer or an unsigned value, and then it's just going to be bytes that follow. And this indicates that it's bytes and there are 11 of them. And finally, this text has again is natively represented, so it basically the 1 byte is going to go to indicate that this is text, and it has 4 elements, and the four bytes, and the serialization.
UTF-8 encoded, or?
I think so, yeah. Yeah.
How do you know the difference between 0418 as a single integer and 04 space 1828?
So which one?
How do you know where the integers are delimited, is what I'm trying to ask.
Oh, so the CBOR standard basically defines that the first number of bits in a byte define what it is, and it might be like a value that fits into this single byte, and then the remaining bits are going to actually represent this value, or you can have the kind of byte header might say, oh, this is actually a text, and this is its length. And what follows is, you know the length, so you know how much you need to go after. And the same with integers. Basically, the first kind of, I don't remember exactly how many bits indicate which case you're looking at.
Is it such then that sort of for each kind of value where you need a number to represent that, they reserve a few bits of that first byte to represent that value if it fits?
Right.
Like 4 bits up to 16 or so.
Something like that, yeah. Basically, there are, I think, like something like maybe 5 bits, or maybe 4 or 5 bits, I think, are remaining past this kind of header, and then you can encode something into it, I think. But it is the spec.
I think it's pretty dynamic. It's like
I
for
mean,
integers, they reserve quite a few bits actually.
Right, I think for integers they reserve a bit more. For doubles, I think they don't at all. For like floating point stuff.
Very short text values to have encoding. Of the
Right,
size.
right. So it very much depends on the particular type. Exactly what happens. Numbers are common enough that, especially like small numbers, are common enough that it just makes sense to try to squeeze as much as you can out of them. Right, so this basically looking at this, it's kind of clear that compared to binary, this is going to be potentially much smaller, and we're going to see examples where it actually is. So now the question is, this is kind of abstract representation of a value. In this abstract representation, like a list, and using just the type system of CBOR that CBOR can natively express. So now, what do you do if you have data in Haskell? What does the Haskell package going to do to try to serialize it? And the idea basically is very simple. If you have a sum type, then the first element is going to be trying to indicate which constructor is encoded. Since you have, you have three constructors, so I think it's 0 to 2 is going to 0, 1, 2 is going to be the first element of the list. And then the remaining elements of the list are basically the fields of this data type. And of course, if your data type is recursive or contains another struct or another sum type, then it's going to be a list, and then one of the elements of this list is going to be another list where the first element is going to be indicated the constructor, and the remaining ones are going to serialize the fields. So it's kind of interesting that by default then the package doesn't do any versioning. Like if I don't really have versions, if I add more fields here, it's going to kind of break because the expectation is different. But you could, if you write things manually, you totally can do it very easily. Just call version along with the constructor tag. And also, it's actually going to, if I only add a new constructor, it's actually going to just work, right? Because the new tag just going to appear, so you're going to be able to decode the old values. It's just that the new values are not going to be possible to decode using the old code, because the tag is going to be unexpected.
If you're honest with ourselves, then we should actually have data types which are used for serialization. And there we only add constructors, so we can only, whatever you have as structure is immutable, you can only add. And deprecation is then essentially handled by the function that projects from the data structure representing the serialized data to the data structure in which you actually want to work.
I think that's one of the approaches. I mean, you can also just say that you write all those instances manually, and therefore you do the versioning on this layer of, instead of deriving generic, you create the instances to serialize yourself, and therefore you encode the versioning there. That's another option as well.
Probably the reason I'm suggesting it is that what I heard, and you can easily correct me, is that at Google you clearly distinguish between the data transfer objects generated from protobuffer, and you should not use them internally for computation. You have to parse space where you translate from them to your internal representation. And I think here Haskell and saying, okay, do the versioning inside mixes essentially the data transfer representation with the computation representation.
So I think it also depends on the particular situation. I mean, one of the things is that do you even need versioning, right? In some cases, if you guarantee that you'll only ever run the same binary on all the nodes, then you don't really need any of that. But yes, in general, like for protobufs, they're not very convenient to use internally for representing your data structures. You really want to use them for the serialization for RPC layer, and then extract whatever you're interested in into your own things that are more convenient to work with. Right. It's I guess the versioning there is also. I mean, it's you basically adding another layer of indirection, right? Because the protobuf is defined in the proto language, and there are specific rules of what you can do and what you cannot do to make them compatible, among versions. So what you're suggesting is kind of basically trying to add this level of indirection of saying, hey, I have a separate time that is going to be serializable, and I control it through there, which is sounds very reasonable.
I'm thinking actually it's a very nice and simple rule, which is say the only thing you can do is add another constructor, because it's really making you honest about you have data that might look exactly like this. In the pattern matching, you get reminded by the compiler there might be old data looking like this. Please explain.
Right. Right. So this is also going to the interesting discussion of where you should be strict and where you should be rejecting things, and where you should be, at which layer should you be kind of checking for any inconsistencies of errors. Like, for instance, protobufs have this, the second version has this optional and required fields, whereas the third version no longer has this distinction. And the reason was that the required fields sound like a kind of good idea, where you do the validation very early on. But in terms of flexibility and long-term maintainability, they're really pain. So nowadays everything is optional in Proto 3. And the reason was that you often have a bunch of additional invariants about your data structures anyway. So you already will need to do some validation on a kind of higher application level anyway. And it's probably better to handle everything there instead of trying to reject things at a lower level when you have much less control. And also, it's just required fields can be, things change, right? What is required now might not be anymore, and now what do you do? So basically that's how serialization, how this Haskell package approaches the serialization of those values. Right, that's what we were discussing. And the interface in terms of what the data type needs to support in terms of type classes is kind of similar to what you've seen in binary, at least on the surface. So you can take a value, create an encoding, and again it's this is actually not a monad. Encoding is just a monoid, so it's kind of unwrapping the put from binary. And decoder is a monad, but the interesting part is right. And then again you have the usual serialize. There are also additional versions that don't throw but return you an error, and with I think using either. And all of it is using lazy byte strings again. So this chunked string byte strings. But I've mentioned that it's similar only on the surface, and the reason for that is that this whole encoding and decoder are actually a crazy idea from Simon, and I'm citing here Duncan. So what those encoding and decoder actually are, they're just representations. They're actually a AST, like a Haskell data type. So this is the idea of using a deep embedding where the recipe of encoding is like a recipe of how do you want to serialize something, and it's represented just using Haskell data types, not using the functions, but just using like an AST. Now you do serialize word, then integer, then a double, and the serialization step comes later in the form of interpreter that takes those tokens instantiated to some values and actually follows the instructions.
So is it written using the free monad pattern, or like is it something similar?
No, it's just more explicit. I think it's not for one it's not a monad.
Okay.
It's just a monoid. And then it's really think about it more of a stream of tokens, of things that you should do, like instructions.
The data structure is isomorphic to a list of a token data type,
Okay.
but all of this is sort of specialized
Right.
to exactly represent the stream of tokens. You're fighting for every indirection. You want to minimize the number of indirections and just put the laziness at the right places.
Right.
Probably will show that.
Somewhat, not all of it, but yes. Basically it's specialized also, kind of trying to follow what CBOR is able to represent, things like that. Right. So again, we have the idea of cheap mappend to construct it, and tokens is basically just a huge sum type with 20 different possibilities, or maybe 10. We basically says, well, now we need to serialize a word and then continue with the remaining tokens. So it's like just a list basically of what do you want to serialize one after the other. Oops. Right, and then again we have the thing that we've already looked at, which is lazy byte string builder. So the interpreter takes those tokens and basically the algorithm is kind of easy. You match on one of those constructors. You extract now I need to serialize a word, and then it's basically uses the lazy byte string builder to actually write the bytes into a byte string, and that's the one that we've looked at, and continues with the next token. And the result is basically this list of strict byte strings, strict chunks. So the byte string builder is actually taking care of things like this build step, allocating new chunks, looking whether you're writing within bounds, and so on.
You also plan strategies to make sure that the first buffer you want to allocate it small, because the time it takes to allocate a buffer from the GHC runtime system is proportional. So not proportional, but it depends on the size of buffer you're allocating. Because the reason there is
for a very large object, I guess maybe they
you can see a difference between like allocating a 1 kilobyte chunk and a 4 kilobyte chunk. It seems to depend on sort of when does it jump over. And then the really large ones matter even more.
That is super interesting. I mean, the GHC usually is using the bump the pointer allocation. So
not for byte strings. Byte strings are pinned.
Oh, okay, they're pinned. Okay,
they're
yeah.
allocated against, well, okay, like a large size there.
Right.
You need, so that the pinned heap consists of
Right. Okay.
the mega blocks.
Yeah.
And then you have this block-based allocation, and that's
Right. So that's where it comes from. Yeah.
But also there's the other thing that
You waste a
might
lot of
well
space.
be that you're allocating a short one, so you don't want to waste bytes. The strategy also what it does is that after you return control to the byte stream builder interpreter, it checks whether you filled enough of that byte stream to be allocated. So if you underfill, then it's actually going to take a copy with the precise filling. You can choose that strategy.
Yeah, I've seen some of the code. Yeah.
If you just use it to write out on the network, you don't care about that. But if you persist these strings, for example, for caching internal, you want to control that.
Right. Yeah, I mean, if you allocate too large from the beginning, you waste a lot of space. So it's kind of one of the, for me, fascinating questions is this really a good idea? So the whole token ASD is actually creating this additional indirection, this additional layer of, you need to build something first, and then you immediately deconstruct it and serialize it. Right? So there's like a whole additional one step in the process. But it's kind of interesting that the performance is really good, and I think the current understanding is that, for one, compared to binary, you don't rely on inlining within the user code. So if you as a user use binary to get good performance, and you kind of the library author cares about what gets inlined into your code to get the optimum performance. Whereas in this case, what the user code is trivial. It's just this stream of the list of tokens and nothing else. And what matters really is then optimizing as much as possible this interpreter, this loop, matching and writing on those tokens. And you only care then about making sure that all the right things or like right optimizations kick in for the interpreter, and that is fully under control of the package author. And the second thing is also that the CBOR itself is for things like double much better designed than binary, so you don't get those crazy slowdowns.
Yeah, I think there's some other things also at play. If you look at this inlining, you're always like, oh yeah, if it's all inlines, then it's all good. But actually, if you think about serialization, then you have a lot of type classes that call each other, and many of these functions are recursive. They can't do proper inlining or recursion boundaries. So you always have either just a function call, or even worse, in some cases you have an unknown function call. So that the most function calls are not created equal in GHC. Function calls to a function where the caller doesn't know the arity of the function are really expensive. And they're actually pretty common, it turned out, for the serialization code.
Ah, I see, okay.
Because you don't know who's your next one, for example. In most cases, you just get passed in that guy, and you call it. If it's not inline, you just don't know. Moreover, with this monad structure, you anyways create on the heap already a sort of a list structure, which is then interpreted as function calls being chained. Right,
so this composition is basically essentially a tree of composed functions,
yes.
right?
And now we can look at how expensive is the function call. Well, if you essentially combine the assembly of what to encode with how to encode it, then your passing around the whole state of the interpreter, all these buffer ranges. So where is my free space? Where do I need? What's my continuation if I don't have any space left? All of this is passed from each of these little functions doing something. With that structure, you have the unknown calls just in the lazy data structure, where it's well optimized. You don't have any function arguments to pass. You just say, oh, go evaluate the weekly normal form. I'll check you afterwards. So it's really, it actually improves locality and then has this nice side effects that the code load goes away.
Yep. Right, another interesting aspect of the encoding, guys, is things like debugging. So if you think about debugging, once you've written a binary format, it's staring at bytes. It's not necessarily pleasant. But with CBOR, for one, CBOR itself is kind of nice because it already carries some type information in its binary representation. So you already have at least a little bit more information. But the second thing, going back to this deep embedding, is that encoding is just an AST, and we have an interpreter to turn it into bits. But if you think about it, it's just an AST. We can write another interpreter that is going to output something simpler, something that you can easily debug or analyze or look at and understand. So there's another interpreter in the library that basically is called flat term. And instead of stream of bits, where in reality you would just stream into those bytes and bits, you just have those term tokens that represent that are basically very, very close to CBOR format, what CBOR can natively represent. And then you can call this, take your encoding, that is your recipe of how to serialize, and you get the flat term. You get the stream of what is the output in a readable form, not in bits. It's in actually Haskell data type that you can look at, print, you can do some assertions on. And similarly to you can look at decoder and provide the flat term and see whether it deserializes it. The decoder is also deep embedded. It's also an AST. So this is an interpreter that tries to, instead of consuming bits, it's consuming just those flat terms. And you can use this whole additional infrastructure to do testing, maybe quick check properties, where if they fail, you can easily inspect things, or you can make additional assertions more easily than looking at particular bytes. So this is for me was quite interesting in terms of you get additional productivity benefits of using something like a deep embedding, where you have more information of. Yeah, I think we can skip that. I just wanted to mention that the decoding is also kind of incremental. It can start before you have all the byte strings, and you can just provide this as things, additional strict byte strings as they arrive. I think this is also exposed if you want to look at this level. So what are the issues? The main problem is that it's not actually released. So it's all shiny, but it's not quite there yet. I think there are still a few things missing. There's missing tutorial. I think there's, as I mentioned, a ticket about a better name for the package. So you comment on if you have ideas. And there are a few things, a few to-dos and fixes within the code base to make sure that all the corner cases are handled. And that being said, I've heard that Well-Typed already used it with some of their customers, so it should be quite okay to use, I think. But if you feel that you have a few hours to spare, feel free to contribute something. Maybe you can get it out soon.
In particular, Syriac.
Right, that would be a perfect opportunity for a project in Zurihack. So if you're looking for one, try this one out. So that brings us to the last package, which comes from Complete. I think Michael Sloan wrote it mostly, but I think it's kind of started with Michael Sloan's blog posts, where he was not happy with binary and looking at, what could you do if if speed was your main motivation? And one of the interesting and fundamentally different choices that Store is taking is to use machine representation wherever possible. So if you have N64, it's going to be just the actual bits as laid out in memory. They're going to be end up in your byte string. So this is super fast because you don't actually need to process. You don't need to figure out do comparisons such as if it's this is a small number, then I can encode it in this way. If it's a larger, then I can encode it in another way. Here you can just say, okay, this is you just copy the memory directly. The obvious downside is that if you have a little endian machine and you send things to the big endian machine, that doesn't really work very well. And again, there's no really lazy incremental things. So both of the previous approaches used this lazy byte strings, where you have chunks of strict byte strings. Here you have just one strict byte string. You just allocate it to fit everything, and you write into it. That's it. So the kind of interface is, again, those two pick and poke are kind of similar. The pattern is not very different, but there's an addition of this size. And the idea, as I mentioned, there's just one buffer. You want to know how much you want to allocate up front. So for a bunch of data types, it's going to be known in advance. For instance, in 64, it's going to be takes 8 bytes. For certain things, you need to provide a function that is computing things. And what this implies is that you potentially might incur a first separate pass of your data structure to know how much space you need. And only then it's going to get the buffer is going to get allocated, and you can start writing to the buffer. In terms of what the pick and poke actually are, they're simpler than the other approaches. So because there's just one buffer, you can get rid of a lot of things. And this package is not actually using the byte string builder at all. And as you can see, it's basically just saying, where can I write? There's just some pointer to the buffer, some information where it ends, where is the current pointer, and that's it. In both cases, it's kind of similar, whether you deserialize or serialize. Right, so some of the cool benefits from using machine representation is that if you have the storable vector, and then serializing is going to be nothing else than just give me a pointer and I'm going to mem copy it, and that's it. There's nothing, no preprocessing. You don't even really look at the elements in terms of what they are and how do you package them on process. Then you just copy everything quickly. And there are some plans to support architecture-independent serialization, with potentially making little endian the default, such that the architecture that is used the most is the faster one. But I don't think it's there yet. Right, so it's kind of interesting that if you look inside under the hood of Store, it's actually quite a bit simpler than both binary and the CBOR one. Both in terms of how it works, in terms of format to some degree, depending on your perspective. It's easy because it's just using whatever is in memory. But if you want to read it with in a different language or not using the Store package, then you need to kind of look exactly what's happening there to make sure that you're doing the right thing. And it's also kind of getting rid of this whole idea of having more incremental approach where you output a stream of those byte strings. Instead, you're just allocating one big one. And so there are still also some interesting-ish, or depending on your perspective again, there are some caveats in terms of this size information. So encoding is going to do this serialization and provide the size needed. And I don't want to show the code, but the fun part, of course, is that if the size is not correct, then things can go quite wrong. So in principle, it's going to try to throw poke exceptions, but if you overshoot, and it can actually write past the end buffer, and therefore potentially sexable. And so the basic bottom line is, if you use the instances generated from, say, the generic instances and combinators provided by the package, you should be fine, because they are very well tested, and they should guarantee that the size information is correct. If you write your own instances, then you should be careful. So I've looked at some of the benchmarks for all of them. So this one is taking one of the benchmarks from the CBOR package, where they basically take, I think, 100 package descriptions as used by Cabal. And this basically means this is a huge Haskell data type with a bunch of sum types, a bunch of information, all the dependencies are there, all the package description, all the links, all the metadata that you put into a Cabal file is represented as a pretty complex Haskell structure. And these are basically results of serializing 100 of them. So as you can see, the reach show is absolutely horrible. Binary is actually doing reasonably well, but it's both CBOR and store beat it quite handily. And what I found quite interesting is that for this particular case, where the data type is quite complicated, and the difference between those two packages is actually quite small in terms of time, but also the size in terms of actual size on disk or serialized size. Store is actually the worst. And I think some of it also comes down to some of the instances that they use. So I think for characters they use 32 bits and things like that. So they're quite expensive in terms of size.
That's actually interesting. What does store do for text?
I haven't looked at it, but I would expect it probably just tries to copy an underlying buffer.
Internally text is UTF-16. So might be that it uses UTF-16.
So for text data type, I would expect that it just copies the buffer. But I think if you have a list like this Haskell string, it's going to need to serialize each of the elements, right? There's no array that you can copy. And I think for that it's using this storable instance, and the storable instance I think in turn is using like 4 bytes per character.
Okay. In that case, I wonder whether the benchmark is that representative, because if this data type is using string, then it represents the wrong way for store to be performed, because most of it is really just management of writing these individual characters.
Well, I don't know. It's more complicated than just text, right? So I guess you would just need to do more benchmarks to really draw strong conclusions. Because also, some of the benefits of store in terms of speed is that if you have arrays, if you have things that you can copy, right? If you have complicated recursive types, then some of the benefits, get lost, I think.
You need two traversals.
You need to do two traversals for a while. The amount of copying, you might find yourself that your memory accesses are going to dominate compared to some of the arithmetic that CBOR is doing to check whether the value is larger or smaller. So I think to some degree it's maybe not representative, but it's still useful in terms of if you do have super complicated recursive data types, then I don't think it's such a big difference between the two. Yes, store might be slightly faster, but it's probably not significantly so. But if you have very simple things, where for instance the size is known up front, where you have only one traversal, then it blows things away. And there are more benchmarks like that for if you have a vector of doubles or vector of numbers, like unboxed vectors. And then again, this is far faster.
Relative to the size of the output, have you looked at the combination? They use one of these very fast compression codecs. So
how do we look
I
at it?
understand Google, most of
Oh,
your data traffic is compressed.
right.
And it seems to me actually that it might make sense actually for nowadays computer architectures. If you don't try to be clever when encoding, you just delegate that task to a general compression algorithm.
Right, and some of them are actually super fast. So it's kind of interesting because protobufs also use, like, in many cases, variants, variable length integers and so on. But that is a true thing, right? There are nowadays really fast compression decompression algorithms. I mean, there are actually a bunch of them developed here in Google Zurich. But there are also some coming from Facebook, like ZSD and so on. So that is an interesting point. I'm not sure exactly. I haven't done many measurements to see. On the other hand, even with something like CBOR, you still might be able to get some benefit out of it. Just because text is text, right? Text compresses very well. So there you go. You still can get some benefit out of it.
Yeah, I'm thinking the other way around. Well, let's rather just use a very fast conversion to sequence of bytes. I'm going to get the same gain for that text as you get on the CBOR, but I don't spend that time sort of transcoding and analyzing.
I don't know. I think for something like this you would need to measure. But even if you do the tricks like CBOR, what I'm trying to say is that even if you do the CBOR tricks, I wouldn't be surprised if you could still squeeze more space if you run through some compression algorithm. I'm pretty sure you still get a benefit. I don't know. You would probably need to measure because then you're running into interesting questions of memory accesses against an arithmetic, right? Most of the time, CPUs actually wait for memory, or quite often they spend a significant amount of time just waiting for memory to provide them to do something. I think you just need to measure, and it also depends on what you're after, right? Is it the speed? Is the speed really the biggest thing, or how much do you value the time compared to the size of the output, right? Are you going to read it from, say, a rotating disk, and then maybe the size matters the most, and you can burn a bit additional cycles to compensate, or is it going to be like super fast SSD, and then maybe you actually don't care that much? I don't know. It's a good question. I haven't measured exactly what would be the right combination. So kind of wrapping up. I guess the bottom line is use one of those. They really look pretty cool, and they're both consistently faster than binary and serial. And depending on your particular needs, one might be better than the other. So if you don't care about architectural independence and you have scientific algorithms that work on a bunch of matrices, then Star is probably going to give you the best performance. If you care about size much more, then CBOR probably is going to win. But in general, both of them really look quite a bit better than the old packages. So if you can, try them out. Any questions? Anything else?
Cool. Thank you very much.
Thanks.
So for CBOR, does the order of the constructors matter, I guess?
Yes.
So you cannot change the order afterwards.
So right, if you use the generic deriving,
Yeah.
yes, it's going to basically look at them, I think, as they are written down, and it's going to assign them. The number 0 is going to indicate the first constructor lexically, and as written. Number 1, this one, and then if you mix it up, then it's going to expect different fields later, and it's going to try to construct a different value, so it doesn't fly. If you write them yourself, in the instance to serialize and deserialize, then you have control over which tag you use, which value you use to differentiate between those constructors. So it's fine.
Okay.
And then you can also go ahead.
No, please.
You can also start with the generic one, right? And then if you figure out, oh, actually I need to do something more crazy, you can always say, oh, now I can write my own. So it's also an easy way to just get started.
Yeah, if you want more control, what you can also do is write a template Haskell function where you give the mapping of constructors to tags explicitly.
Probably, yeah.
We used to have something like that for sort of backwards compatibility.
Mhm.
We were explaining like the new data type, how does it actually map? And this is another reason for me why I actually would like to have two separate data types, because like even just the access control and who is allowed to make changes to the serialized representation, you need a very different review.
Right, I
policy.
mean, you might want to do much more rigorous testing if you do changes to serialized stuff, right?
Yeah,
Whereas for internal data types, if it compiles, it's fine, right?
Yes, and there again, like this rule enforcing just adding constructors,
Yeah,
that's
yeah.
one which you can easily enforce just on a source control level.
Right.
So I like it.
That's a good point.
On a related note, there are languages where this is built in, and I just think of Protobuf as an example. This access control on the source code level is built into the language if you use something like Protobuf.
How does that work?
They use labels for constructors, and you can only, if you change your message, then you can only use higher label numbers. So
You could change the source code such that you just reassign a label, couldn't you?
I guess, yeah, right. Yeah, I think that's right. On that note, is there a usable Haskell implementation of Protobuf yet?
So there's the ProtoLens library. I think it was released. I haven't used it, so I can't give you a first-person recommendation or otherwise. But I've talked with some people that were quite happier with it than the old one, and it seemed quite nice. And I know that some people internally use it. But as I said, I haven't actually tried it, or I haven't seen any benchmarks or anything like that. But try it out.
Very well. I guess that sort of concludes it, unless other questions are. There's the option of going to Jim's Pizzeria. You guys are going to have pizza, hopefully outdoors, but let's see whether they do outdoors. And yeah, is there anybody who hasn't signed up for Syriac and would like to sign up, even though registration is closed?
You should.
Talk here.